So a reminder, we're talking about simplicial homology. And last time we wrapped up by noting that if two spaces, two topological spaces x and y, are homeomorphic, so bicontinuous maps between them, some continuous map f from x to y with some inverse g, say. If x and y are homeomorphic, then the corresponding homology groups will be isomorphic for all n. And the proof for this was quite straightforward. The way we think about it is, what is homology? Well, it's by looking at these quotients of the kernel and the image. But if you look at the level of Cn, you have that if you have some space x, then you're just looking at maps of an n-simplex into x. This is a simplicial n-simplex, a map of xn into x, a continuous map. And so if you have a homeomorphism between x and y, you have continuous maps going both ways, then this will exactly correspond to a map from xn into y, right? So you have this nice correspondence between these maps. So on the level of your chains, these are equivalent, and so then it goes all the way down to the level of homology, they're equivalent. So this is pretty straightforward. This is what we talked about last time. If it's homeomorphic, then the homology is the same. Today, we're going to try to generalize this. So the big result we want to prove today is that if x and y are homotopy equivalent, spaces, then the homology groups are still isomorphic. So homology cannot detect things up to homotopy equivalent. So another way, homology is invariant of homotopy equivalence. So this is broader than being homeomorphic. Homeomorphic is quite tight. You have to have a nice, continuous map and inverse map between two spaces. The spaces look the same. Homotopy equivalent, they don't really have to look the same, right? So can you maybe remind me of an example of two homotopy equivalent spaces? And we can remind ourselves quickly what this means. So what are two spaces that are homotopy equivalent? You tell me, favorite two homotopy equivalent spaces. S1 and S1 cross I. Yeah. So here's S1, and here's S1 cross the interval, a cylinder, S1 cross 0, 1. And the claim is that these are homotopy equivalent spaces. So how do you show that two spaces are homotopy equivalent? Well, in general, what you're looking for, in general, if you have spaces x and y, so in general, if you have x and y, to be homotopy equivalent means you have some continuous map f from x into y and some map g from y into x, such that when you look at the compositions, f composed with g and g composed with f, f composed of g means you're beginning with y, so you do y to x, then x to y. It isn't necessarily exactly the identity on y, but it's homotopic to the identity on y. And likewise, g composed with f will be homotopic to the identity on x. And here, there's a very natural map from S1 into S1 across the unit interval, which is just the inclusion map. We can just include S1 into the bottom. And then the map going back can be like the smash map that just smashes it all down onto the cylinder. And then you can think okay, what would these compositions be? Well, if I include and then I smash, it is just identity. It's exactly identity, right? So this way, doing F and then doing G is exactly identity. However, if I first smash, giving me S1, and then I include it, it's no longer identity, it's the map from the cylinder to the bottom of the cylinder. And that's not identity, but it's homotopic to the identity, where there's a clear homotopy that's just shrinking the cylinder down over time, right? So this is what it means to be homotopy equivalent. Very good. Okay, so these are not homeomorphic, but they are homotopy equivalent, and therefore these should have the same HNs. In this example, we know that HN of S1 is just a copy of Z when n is either 0 or 1. 0 because it's path connected, 1 because you have this circle here, and 0 for n greater than or equal to 0. We've calculated this in the past. And so what this result will tell us is that the same is true for the cylinder. Hn of the cylinder, S1 cross 0, 1, has the same homology. Good? That's what we want to prove today. Okay, this is going to take some work. So we're going to spend all of today's class building up to this result. But hopefully it's clear what the statement is. And the way we're going to prove this is, what I'm first going to try to argue is that if I have some map from x to y, that from this map, it induces a homomorphism between the two HNs. And then we'll need to show that in the special case where this map has a corresponding G, so there's a homotopy equivalence between them, then in fact it's an isomorphism. But for now, I just want to show you, if you're given a map between spaces, then you can, from that, this induces a map on homology. So what I want to argue is that this induces a map on homology. And for us, we are now working with singular homology. So whenever I do proofs, I almost always use singular homology because it's much better situated for proofs. Okay, so let's remind ourselves how singular homology works, right? If I want to calculate the singular homology of something like x, what I'll do is I'll look at my Cn of x, where this is the abelian group whose basis is all of my simplicial n complexes, right? So the basis of this guy has basis comprising all of the maps from an n complex into x, all continuous maps. But they can be singular maps. They can have irregularities, right? They can map onto themselves or map all down to a point or anything like that. So this is the abelian group where this is the basis of it. And just as you can do it for Cn, you can do it for any number, Cn minus 1, whatever you like, Cn plus 1, Cn plus 1 of x, and so forth. And then we have a boundary map between these guys. Sometimes I'll give you a subscript to emphasize this is the boundary map from Cn to Cn minus 1, so it's the boundary map with the n subscript, or here I'll use subscript n minus 1. Sometimes I'll just put the boundary symbol. But from this, we then go and we define homology, right? So once we have this, we then define Hn of x to be, maybe you can remind me, the kernel of this boundary map over the image of this boundary map. Right? Okay. That's how you do it for x. You do it the exact same way for y. So for y, we can also create this chain complex and define homology in an exactly analogous way, where we have Hn of y is the kernel of the boundary on n over the boundary, the image of the boundary at n minus 1. Okay, maybe there's some ambiguity now because I have these boundary symbols I've called the same thing. So if you really want to emphasize the distinction, you could call these like the boundaries on the x's and these on the y's, and emphasize this is the kernel up here of these boundary maps on x, whereas this is on y. But hopefully it's clear from the context that that's what I mean. Okay, so that's how I define my homology. And so what I ultimately want is I want some function from Hn of x to Hn of y that's induced by f. So what I want is I want some f star. That's what I want to define. And the way I'm going to define that f star is first I'm just going to define it as a map from Cn of x to Cn of y. And so I need to call it f something. I don't want to call it f star because I want to save that notation for homology. So often this little sharp symbol is used, f sharp. That's the sharp symbol, yeah? Music? Yeah, f sharp? Okay. So here's f sharp. So how do we define f sharp? So like we think right here, things in here, well the basis of things in here are maps from delta n into x. But things down here should be maps from delta n into y. So what should f sharp be? How can we define f sharp? Well, let's just say what it does to one of these basis elements. If I have some basis element sigma, so right now that's sigma, just think it's a map into x. But I want it to be a map from my in simplex not into x, but into y. So really I want it to be a map from here to y. How do I do that? Well, I know I can go from x to y using f. So I'll just define the map from here to y to be f composed with sigma. So we'll just define this to be f composed with sigma. Okay, so this is just composing with f. Now instead of mapping into x, you're mapping into y. F is moving things from x to y. So that works. Okay, right now I've only defined it on the basis elements. I want to define it on all of my n chains, and I want it to end up to be a homomorphism. So how do we do that? Well, we just extend it linearly. And extend linearly. That is, you just define f sharp of some linear combination of some, whatever your coefficients are, ci, sigma, I'll use some script I to denote the different sigmas. These aren't powers, but subscripts. To just be summed over I, just to be the sum of ci times f sharp on sigma I. So you just extend it linearly. These are just linear combinations of things in your basis. Now we define on the basis elements, you can define any linear combination of them. Okay, great. So we defined f sharp this way. And there's nothing special about doing this in Cn. You can do the exact same thing for any, Cn minus 1, Cn plus 1, wherever. So there's analogous f sharps on all of these. Okay. But what I want to do is I want to really think like, okay, how do I now get a map from here to here? And here you have this boundary operator. So let's think about how boundary and f play together. What is f sharp on, say, the boundary of some sigma? So let's say you begin with some sigma in here. You take boundary of sigma, and then you take f sharp of it. Okay, so I start out with some sigma here. I go over I have now the boundary of sigma. And now I want to map that down to f sharp of the boundary of sigma. Let's see what we can say about this. Well, first of all, do you remember how we calculate the boundary of a simplex? So the boundary of a simplex, just this piece, the boundary of a simplex is just defined to be the alternating sum. So this is the alternating sum, so sum over I of -1 to the I of sigma restricted to, okay, well, I guess in this example, I'm starting off in n+1. That's going to get a little bit messy. So let's instead change this picture so I begin with a simplex that's an n-simplex, a singular n-simplex. So we'll look at the boundary of that guy and then map him down. I think that will make this work come out a little bit nicer. So that my subscript goes up to n instead of going up to n+1. It's just I look at this n-simplex, v0 up through vn, and I omit some vi in the middle. So now it's an n-1 simplex. Right? So by mapping the boundary over, it's an n-1 simplex, but it's an alternating sum of those. So this is a linear combination, so sure enough, he lives in here, of these guys. And I'm taking f of this. I'm taking f of that whole thing. But we've just said that when you try and take f of some linear combination, we had extended it linearly so that this is just a linear combination of f on each sigma I. So this will exactly just be the sum of -1 to the I of f sharp on sigma restricted to this face over I. v0 omitting some vi up to some vn. But that is precisely just the boundary of f sharp on sigma. So since we defined f sharp to be linear, it commutes with the boundary operator. Which is saying that going from here over and down is the same thing as first taking f sharp, as first going down to get f sharp of sigma, and then taking the boundary, and then going over and getting the boundary of f sharp of sigma. Yeah? So you can either travel over the boundary, then do your f sharp, or you can first do f sharp and then do boundary. And that's not just true in this block, it's true in any block, right? It's just a different count on the indices. So this diagram here introduced the convention of saying this diagram commutes. What I'm saying is this diagram commutes. Meaning, when you have two different paths, over down and down over, they both give you the same thing. Okay, is that good? Are we happy? So f and boundary are commuting. This diagram is a commuting diagram. So now let's think about what's going on here in homology. Let's say we begin with some element of hn of x. So we can think of that element as being some element alpha that lives in the kernel of this boundary map. So here's this boundary map. I'm in the kernel of that boundary map. So what kind of thing is alpha? Well, I know the boundary of alpha is 0. So this is just telling me that the boundary map on my alpha is 0, right? It's in the kernel of the boundary map. So what do we call those things? Do you remember? Things that have no boundaries, it's just called a cycle. I don't know if I made this very clear in previous lectures, but alpha is just a cycle. Okay. Maps to 0. Now, what I want us to think about is what is f star of alpha? Well, when I think about f star of alpha, I want to know, is f star of alpha in this kernel? Because that's where I want it to be. Right? So what is f star? Well, let's think, what does f sharp do? what would f sharp do to alpha? So if I have f sharp of alpha, I want to know, is it in the kernel? So what does this boundary map do on f sharp of alpha? We've just said that's going to be the same thing as f sharp on the boundary map of alpha. And the boundary map of alpha is 0 because it's in this kernel up here. So since he's a boundary, this is 0. So it's f sharp of 0. And since it's linear, that comes out to be 0. So sure enough, f sharp of alpha ends up being in the kernel down here. So we've just seen that this map f sharp takes a cycle to a cycle. It takes things in the kernel up here to things in the kernel down here, precisely because f sharp commutes with the boundary. Now, the only other thing you want to check is, what does this operation here mean? This does mean everything up here is defined up to some indeterminacy. It's defined up to things in the image of the boundary. So you can think this is really an equivalence relation on alpha, where it's alpha plus anything in this image, right? So really you should think the things in Hn are of the form, things in Hn are really things of the form alpha, which is in the kernel, plus things of this form, maybe like boundary map of beta, something like that. Something in the image of the boundary map, n-1 boundary map. It's an equivalence relation of everything of this form. And what we want to check is that this equivalence gets respected, right? Well, let's think about pieces of this form. What can you tell me about what f sharp does on things in this image? Well, since f sharp commutes with boundary, this is precisely just the boundary of f sharp of b. So he's still in the image down here. So alpha, so this whole thing ends up mapping to f sharp of alpha plus some indeterminacy, which is still in the image though, the boundary of f sharp of beta. So sure enough, it's a map from Hn to Hn. Okay, so we have boundaries mapped to boundaries, and cycles mapped to cycle, and boundaries mapped to boundaries. And so it's well defined. So whenever you have a map on CNs that sends boundaries to boundaries and cycles to cycles, it translates over to a map on Hn. And that's what we just verified. When f commutes with boundary, it has these nice properties. It preserves both cycles and boundaries, so therefore induces a map on Hn. So f star of an element here is exactly whatever f sharp does to it, up to the indeterminacy by quotient out by the image. So let me pause. Is that clear? Happy? Questions? Yeah. What did I do wrong? This is a plus. Where? Somewhere there's a mistake you're claiming. This image? Oh, yes, this should be the image. What did I do? This should be +1. Yes, of course, this is +1. This is +1. Thank you. Yeah. So forgive that. Okay. If you got lost in the weeds here, all I'm saying is if I have a map from x to y, then by just composing with that map, I now, instead of setting a simplicial complex into x, I'm setting it into y, and we checked it satisfies all the structures, so that now things in Hn are going to things in Hn and y. Things in Hn of x are going to things in Hn and y. But really, you can think it's just composing with f. That's the map. Okay. Good. So now we at least have that if you start out with a map from x to y, you get a map on homology. But we want to prove something a little bit more. Ultimately, what we want to prove is this result. So let me just write that as a theorem. What we want to prove, and now maybe we can write it more precisely, is that if I'm given two maps, okay, I guess there's a, okay. Here I'm trying to say, if x and y are homotopy equivalent, then the HNs are isomorphic. We will prove this. Here's how we'll prove it. First, I'm going to prove this. If x and y are homotopic maps, if f and g are homotopic maps from x to y, where f is homotopic to g, then the induced map on homology for f and g are the same. So f and g both induce maps, so just write f induced map is the same as g induced map, where these are both maps from hn of x to hn of y for all n. That's what I'm going to show. Once I show that, let me show you how you move from here to the result. So what I want to move to is this corollary of saying, if x and y are homotopy equivalent, then the HNs are the same. Well, what does it mean for x and y to be homotopy equivalent? If x and y are homotopy equivalent, that means that there exists some f from x to y, and there's some g from y to x, such that f composed with g and g composed with f are both homotopic to the identity map, where f composed with g is the map that begins at y, and g composed with f is the map that begins at x. I was like, if x and y are homotopy equivalent, then say your f induces in isomorphism between hn of x. So f from hn of x to hn of y. We already know this is a homomorphism, but now I'm saying this is in fact an isomorphism. That's what I want to show, right? That you get an isomorphism between your homology. So how do we move from the one to the other? How do I move from here to here? It shouldn't take too much space because it's a corollary. So it has to fit within half a board, or else it's called a, it's not called a corollary. That's the rule to be a corollary. You have to be able to do it in less than a board. Okay, well let's just suppose we have these two spaces, these two maps, f and g. And let's say we have the setup here. We have maps f and g. Then we know we get these induced maps. We have induced homomorphisms where f induces some map from hn of x to hn of y, and g induces some map from hn of y to hn of x. Then what I want to say is consider f star composed with g star. What is this? Well, let's go back and think on the level of chains. So, and same thing, I'm going to do g star composed with f star. So we can do this one first. Let's do this one first. I like doing this one first. So what is f doing? F is a map from x to y. So f is some map from x to y. and I have some map from delta n into x, some simplicial map sigma, right? So we say my f star is just this composition. So my f star is just f composed with sigma. That's what f star is. Now, what I want to do is I want to come and take g star of this. G star of this guy would be introducing the map g into x, and then doing g star should just be g composed with f composed with sigma. But g composed with f composed with sigma is equal to g composed with f composed with sigma. And this is just g composed with f star. This is showing that this is just equal to g composed with f star. Right? What? I mean, this diagram, it all just commutes. We're just composing maps. And when you compose maps, it's associative. So by the associativity of composition, these are equal to each other. And exactly analogous with switching the x's and the y's around, this is just f composed with g star. But once you believe the theorem, which you will in 10, 15 minutes, once you believe the theorem, then you should believe that since f composed with g and g composed with f are both identity maps, that this is equal to whatever map the identity map induces on homology. Right? But now let's think like what map does the identity map induce on homology? This, one is going to be the identity map on x, and one's the identity map on y. So let's do this one. Let's think about the identity map on x. Now here's x, here's some sigma, it's mapping some delta n into x, and then you have like identity map from x to x. So this becomes the identity map composed of sigma. Well, friends, that's just sigma, right? So the identity map composed of sigma is just sigma. So the induced map of the identity map is just the identity map. It just leaves sigma alone. And likewise, this is also just the identity map. So what we see here is that this induced homomorphism has an inverse homomorphism. And so in fact, it's an isomorphism. That's what we've shown. Okay. So maybe this is a little bit in the weeds, but the point is, once you know that homotopic maps have the same induced map on homology, then you get this for free. So what I need to do is convince you that if you have two homotopic maps, they induce the same map on homology. That's going to take some work. But that's what we're going to do for the rest of today's class. So let me come back here. This might be like a 3-board proof. So here we go. Let me rewrite the statement. What we're trying to show, it's a corollary. To get the corollary, I'm trying to show the theorem from which a corollary follows. We're trying to show that if you have some homotopic maps f and g, which are maps from x to y, kind of squishy notation together here, then the induced map f star is equal to the induced map g star, where both of those are just maps from hn of x to hn of y. Okay? Okay. So let's suppose we have this. Suppose you have some homotopic maps, both maps from x to y. We will show, we will construct give me an outline of how we're going to do this. We will construct a map P such that G minus F, these are the induced maps on the level of chain complexes, is just equal to the boundary of P plus P boundary. Okay, so this might be kind of weird. So maybe I should draw this diagram again, and we can see what's going on here. So let me draw this again. We have these abelian groups. And I can think of my G or F sharp as mapping from any one of them down to the corresponding groups on Y. So say I can think of them here, where here coming down I have some map G sharp, and I also have some map F sharp. Okay, there's two maps coming down, G and F. You can think about either one. Or if you want, you can take the difference and just think about the single map coming down, G sharp minus F sharp. Now I'm going to construct some map P. So it's like, what should P be? A map from where to where in order for this to even make sense? Like, P is going to map from where to where. Well, here it's like, I'm going to do a boundary operation and then do P. And then here's like, I want to do P and then do a boundary operation. But that should be the same. Like in both those cases, we should be going from the top to the bottom. Right? So boundary is just moving over. So P should be moving from top to bottom. So this should be something with an X. And this should be something with a Y. But now we got to get this all to work out. So here's another way you could write this relationship that maybe makes this clearer. Another way to write this is that the boundary of P is equal to G sharp minus F sharp minus P boundary. I'm going to define P to move me up one index. What you're going to see that does then is that if something like this is my P, then you would have the boundary of P. The boundary of P would be coming down P and then going along a boundary map. Whereas G sharp minus F sharp minus P of F star is going to be doing minus P. I'm sorry, this is P, no, this is boundary composed with P. Oh, good, okay. First I'm doing P, then I'm doing the boundary. Here, first I'm doing the boundary, then I'm doing P. Good, okay. So here's boundary, here's P. So, either way you think about this, boundary composed with P is a map from Cn of x to Cn of y. Because first doing P takes me to Cn plus 1 of y, and then doing boundary takes me to Cn of y. This guy is a map from here to here, And these guys are all also maps from Cn of x to Cn of y. G is, G sharp is, F sharp is, G sharp minus F sharp is, and so is first do boundary, then do P. So either way you think about these are maps from Cn of x to Cn of y. So I'm just making a note here that this P we're going to have to define is kind of weird because it's going to take us from simplicial n simplices to simplicial n plus 1 simplices in x to in y. Right? So we'll have to come back and define that in a second. But the key is once we define that, it satisfies this relationship. I'm going to build it to satisfy this relationship. Now let's think, like, what's the advantage of satisfying this relationship? Let's think about our map, our induced map on homology. Here's Hn of x. Here's Hn of y. Hn of x is defined to be the kernel over the image n plus 1. Same thing for Hn of y. And what I want to do is I want to think about the map between these defined by the induced map on G minus the induced map on F. Let's analyze this map just like we did before. So what I'll do is I'll begin with some cycle alpha in the kernel. It's called a cycle because cycles are things that have no boundary. When you try to take the boundary of a cycle, boundary 0, right? So I began with some cycle alpha. Okay, let's think about that cycle alpha. What does this guy do to alpha? Since we're just thinking of this on the level of living inside of Cn, what I'll do is think about what is G sharp of alpha minus F sharp of alpha. Well, once we've constructed this map P that satisfies this property, this will just be the boundary of P of alpha plus P times the boundary of alpha. Since this is a cycle, the boundary of alpha is 0. This is 0. So this whole piece will die. We'll make sure P is defined linearly, so P of 0 is 0. If that whole piece dies, then G sharp minus F sharp is equal to the boundary of something. What that means is this whole thing is in the image of your boundary. P takes it, so you're in Cn plus 1, that's why I bump up by 1, and now you're in the boundary map, boundary n plus 1. Which means that this comes out to be 0. Well, it dies in this homology, right? G sharp minus F sharp dies down here. So what that gives you is that the induced map of G minus F is just the 0 map. Takes elements up here in this kernel down to this image, so they're dying. Thus, these are the same induced map. Okay. Once I can define a map P that has this property, we then get the result. I'm emphasizing this because note, whenever you can find some map P like this, it means that G and F induce the same maps. So I'm going to build a particular map P now. But whenever you can construct any map P, whenever you can construct any map P that has this property, the induced map for G and F are the same. And we're going to come back and use this property a number of times. So today I'm going to construct a particular P for the purposes of this problem. But in general, whenever this property is satisfied, it means that G and F are satisfying the same, induce the same homology. So important note. So what I need to do in the last, 5-10 minutes is actually to tell you what this map P is. Before I construct P, let's remember the context that we're in. F and G are homotopic maps. So what that means is you expect there to be some homotopy that is moving from little f to little g. So there exists some homotopy. And I don't know what to call it. I'll call it big F, which is a map of x cross 0, 1 into y, such that at time 0, you have map little f. Little f is just what this is at time 0. So, big F of any x value at time 0 is going to be giving you the little f map. And big F of any x value at time 1 will be giving you the map G. So when we go and we induce these maps, G sharp and F sharp, the way you would typically do this is you would say, well, you have some map, say, your F or your G, whichever one it is, let's just do it for F, from X to Y, and you have some simplex sigma that maps into X, and so the induced map F sharp is just going to be F composed with sigma. But now it's a little bit trickier, because now we are thinking of this homotopy, so we're adding a dimension. This homotopy is a map from x cross 0, 1 into y. That's what that big F is. And so what we're going to think about here is instead of having my simplicial n complexes be maps from just delta n into x, I can think that the maps of delta n cross 0, 1 into x cross 0, 1. So this is like sigma cross, well, okay. So this map here is kind of a funny map because it's like sigma cross 0, 1. It's just whatever this map is and then whatever the value t is there, maps that value t there. So the induced map on F would be F composed with sigma cross the interval 0, 1. So what is an n simplex cross 0, 1? Like this is kind of a weird thing that we have here. What happens when you have it in simplex and you cross it by 0, 1? Like, let's take a 1 simplex and cross it by 0, 1. A 1 in simplex would just be v0, v1. But when you cross it by 0, 1, we get something like this. When you have a 2 simplex cross 0, 1, that's just going to be a triangle. v0, v1, v2, v2. Cross 0, 1. Will look something like this now, right? And we can continue. You know, it gets harder to draw the higher you go up. But what I want to point out is that when you have these in simplexes cross 0, 1, the result is still a simplicial complex, where here you can just draw an extra edge, and then it's just the union of two. It's just two simplices glued together. And here you can, you know, dissect your edges however you want. This one's a little bit tougher to draw. I want to decompose this as a bunch of tetrahedron. Do you see a way to do it? It's a little bit tougher to draw. I think this works. Something like this. I should label these other points. So this is like W0, W1, and this is W0, W1, W2. But note what this is now. This is just a union of two simplicial complexes. One is V0, V1, W1, and the other one is V0, W0, W1. Whereas over here, we have also a union of several simplicial complexes. One is, okay, let's try and write them all out. One is I claim V0, V1, V2, and then W2. So do you see the complex that corresponds to these 3 points? It's this tetrahedron right there. Union V0, V1, W1, W2, where you have V0, V1, W1, and W2. So do you see this tetrahedron with those 4 corners? And then you have V0, W0, W1, and W2. V0, W0, W1, W2 is just that tetrahedron right there. Okay, so delta 1 cross 0, 1, a 1 simplex cross 0, 1 is just a union of two simplices. And a 2 simplex cross 0, 1 is a union of three simplices. And notice this like really nice way of naming the simplices. The convention I follow is like you just list V0, V1, and then one of the W's. Or one V and then both W's. Or maybe here it becomes clearer. You can go all the way up to V2, then go to W2. Or you can stop at V1 and then shift to W1 and keep going up. Or at V0, you can shift to W0 and keep going up. So there's a nice convention for how we name these things. Let me define P now. Now that you understand that this is what a delta n cross 0, 1 looks like, we can define my map P, which goes from Cn of x to Cn plus 1 of y as follows. P of sigma, so this is an n simplex, will be a alternating sum of f composed with sigma cross 1, because that's where we said this has to look like. F is a homotopy, so it's eating in values in x cross 0, 1. So when you do f sharp on it, it's just f composed with that. But then we're going to restrict this to an n plus 1 simplex. And so it'll be defined by just calculate this on each of the n plus 1 simplices that make up delta n cross 0, 1. So I'll just look at whichever n plus 1 simplex you would like to. They all follow this form of v0 through vi, then shift to wi through wn. Notice it says wn, but this I was double counted, so this is an n plus 1 simplex. So this is moving you from n simplices in x to n plus 1 simplices in y. That's how you define your P. And what we need to do is we need to check that P satisfies this property, that P boundary plus boundary P will come out to be G sharp minus F sharp. Now that I have a definition of P, this is what I need to check. So I'm going to check this. Give me, what? 5 minutes I can check. I can check it in 2 minutes or 5 minutes. Okay. We can check it for this guy, which will be really easy, or we can check him in this guy, which will take a few more minutes. Which one do you want to do? The quick one? Let's do it in the quick one. Okay. I'll check that this relationship holds in this case, and then you should check that it also works in the other case, and then you should sit down and follow how Hatchett does it with all of the indices in the general case. But let's just unpack this definition to make sure that this actually works. There's a nicer way of writing this relationship, which is writing this boundary here. And this is how we're actually going to check it, P boundary. So this is how we're actually going to check it. What is the boundary of P? Okay, let's just calculate the boundary of P on my one simplex V0, V1. So that's the boundary of P is defined to be the alternating sum of F composed with sigma cross I restricted to, and then you just, in this case it would just be V0, V1, W1 minus F composed with sigma cross identity restricted to V0, W0, W1. And now, what is the boundary of this? The boundary of a in simplex is just, in this case, a two simplex is just the alternating sum. So the boundary of this should also be an alternating sum, where the first piece is just omitting the first guy. So it'll just be F composed with S sigma cross boundary restricted to omit the first guy, V0, giving you just V1, W1, minus, because it's alternating sum, omit now the second guy, V1, so it becomes F of, okay, I'm getting tired of writing this so often, sigma cross 1 restricted to V0, W1 plus alternating sum, so minus then plus, f composed with sigma cross 1, omit the last guy, which is doing the boundary operator, v0, v1. Minus, now we're doing the boundary of the second guy. Okay, what's the boundary of the second guy? Boundary of the second guy is, again, alternating sum. So f composed with sigma cross identity. Remove the first guy, v0, giving you just w0, w1, plus f composed with sigma cross 1, omit the second term, v0, w1, minus f composed with sigma cross 1 of omit the last term, so v0, w0. Okay, things should start canceling. Does anything cancel? Maybe in this case, not much does.
V0, W1.
Where's your v0, w1? Ah, beautiful, glorious. This v0, w1 is plus v0, w1. This is a minus v0, w1. Those cancel. Okay, what else do we have? Look at this case. This is when you're restricting to just the bottom. v0, v1. The bottom, the homotopy, but just done on the bottom, is just little f. This is just little f. Remember, the homotopy was it crossing I. And we said like the homotopy at the bottom was f, and at the top, at 0 was f, and at 1 was g. So on the bottom, this is little f. So this term here is precisely just little f composed with sigma. And when you're just at the top, this term here, this is precisely just the top. This is a homotopy, so it's going from little f to little g. It's just little g composed of sigma. So now all we have left are these two terms. But what are these terms? It's just f on here minus your f composed of sigma cross I on here. And what is that? Well, that is the boundary of this one simplex, your v1 minus v0 cross I. These other two terms, this term and this term, are exactly that boundary term. So this is exactly, whoops, I have a sign error.
It should be because one side minus the other side is the boundary of one simplex.
Did I? But this is this boundary. And my f is positive, but I wanted my f to be negative. And I wanted my g to be positive. So maybe somewhere I mixed up my signs. Did I get my signs mixed up? Oh no. We did all this work just for the signs to be backwards. This was good. That's what I want to show. The boundary of P is this. So here, where I omit this, but I want this to be negative. Oh, it seems to be a sign error. Well, I mean, it just comes out to be 0, so it doesn't matter, like up to sign. Right? Just do g on bottom, f on top if you want the signs to agree. So here I instead had it by mistake as f sharp minus g sharp, but up to sign it doesn't. The argument still works. And then these two are exactly just the boundary of. So there's a sign error on all of this. Somewhere I made a mistake with signs. It's just the boundary, is just P of the boundary. of sigma of V0, V1. Because this guy would just exactly come out to be P of V1 minus V0, which is exactly what these terms are, because this is crossing your V1 by 1, and this is crossing V0 by 1. Okay, so sorry about the sign mistake. And this is quite in the weeds. So, you know, if you didn't follow all these details, it's fine. The big takeaway is when you satisfy this property, if you can find a map that satisfies this property, then G and F induce the same homology. So that's the big takeaway today. So I've gotten to the weeds. Sorry about that, but that's it for today.